Teichmüller, speaker of this program. Okay, so what is the broad goal? The broad goal is that we want an explicit analogy between non-uniform lattices in SL2R and mapping class groups. Okay. So I will try to explain the results for SL2R first, and if time permits, I'll say a little bit about the moduli space of curves. Essentially, whatever results I will write in this case, more or less with some extra hypothesis, will carry over in this case. So, okay. So let G be a non-uniform lattice. In SL2R, I'm going to let X be the quotient surface for the action of G on H2. So this is a finite area, non-compact.
So come on, G?
The more I have some problem with the Greek letters actually. Yeah, I know. I have some problem with the. I just want to call even this guy G later on. It's just easier to remember these things. If I start writing gamma, I'm going to surely switch to G at some point, and that's going to create confusion. So, so this is finite area, non-compact hyperbolic surface or orthofold. All right, let's draw a picture. This is what the surface looks like. Here's the surface. So I'm going to consider the thin part of the surface. So there will be some epsilon small enough so that if you look at all points where the injectivity radius is less than epsilon, this set consists of just neighborhoods of the cusp. So there are some number of cusps here, and the thin part of the surface just takes out cusp neighborhoods. Right. And then this is the thick part, which I'll call W. All right. The lift of this picture in the upper half space model, so this is R, will look as follows. So these cusp neighborhoods lift to a horoball packing. And of course, the action of the group in the horoballs is by translation. So in this case, it's something from G plus F. Up here, at least, for the horoball at infinity. Okay. Going to set up, let me just write it here since board space is at a premium. So I'm going to define the total excursion till time t for a recurrent geodesic. So geodesic array gamma is said to be recurrent if it comes back to W infinitely often. Okay? And so what is the total excursion? So up here in this picture, we start off from some point x naught, and we have a geodesic that goes off, and who knows what it does. But it keeps coming back to the thick part infinitely often, the lift of the thick part infinitely often. So suppose gamma process intersects, suppose gamma intersects some horoball. So we define the excursion of gamma in H to be the distance, the thick part distance between the entry point and the exit point if gamma of t is already left the horoball, or otherwise we define it as a partial excursion, which is simply, so I guess I want to take here P to be the closest point projection from H2 to W hat tilde, is the closest point projection. And if gamma is in the horoball, the gamma t is in the horoball, then we take the excursion of gamma in the horoball to be the distance between, excursion of gamma in the horoball to be the W hat distance between the entry point and the projection, so P of gamma of t. It's just to get the definitions right. Okay, so this means that the point at time t is still inside the horoball. So it's a partial excursion. We have not gotten out of the horoball yet. Okay.
Yeah, what does this distance in the thick part mean?
What does it mean? So you should think of these numbers as analogs of coefficients of continued fraction expansion. And you will see in a minute that this actually can be very, very precise for the modular surface. That these numbers will actually, up to a uniform additive constant, will be the same as coefficients of the continued fraction expansion. Okay. So now there is the word random geodesic in the title, and I'll tell you two notions of random geodesic. So what is a random geodesic? So the first notion is to use the Lebesgue or the Liouville measure. So the unit tangent ball at a point x0 can be identified with S1. We take the Lebesgue measure on S1 and so sample the initial vector V of gamma naught by the Lebesgue measure on S1. That's the first notion of random. The second notion of random comes from doing a random walk on the group. So we take, can everyone see this? We take a finitely supported random walk on G. So let mu be the distribution for the random walk. We look at the nth sample path, which is a random product where each gi is sampled by mu. We project this random walk into the hyperbolic plane and then consider limits as n goes to infinity. So with probability 1, the sequence, as n goes to infinity, the sequence, when we take this random word in the group and act it on the base point, this sequence converges to some point in S1. Okay, as n goes to infinity. So this defines a harmonic measure H on S1. So what does this measure tell us? It just tells us the distribution. So the measure of a set A is the proportion of sample paths that converge into it. That converge to it. Okay, so we have these two measures on S1. We could use.
This is an ambiguity. Which point do you pick?
Oh, the base point?
No, for the projection. From H2 to W tilde.
There is an ambiguity. No, I'm confused. Why is there an no? Just the vertical geodesic is going to achieve the minimum distance to the boundary. Yeah, it's a convex set. Yeah, you just take In this picture, you just take the vertical geodesic ray. That's the shortest path to the boundary. All right, so we have these two measures on S1. So we could sample our geodesic rays by picking the initial direction with respect to these two measures. So that's the two notions of random I want to consider. And so we want to, I didn't define, I told you I would define total excursion. I just defined an excursion in one horoball. But the total excursion is just going to be, since I'm running out of space, I'm just going to erase one of these lines. Let me just erase this line here. The total excursion of gamma up to time t is, you just add up all the excursions that we see. So you take the sum of the excursions up to time t, k is less than or equal to n, so where h1, hn are horoballs, gamma intersects till gamma d. So we just added up all the excursions. That's what I mean by total excursion. So the theorem here, so I should have mentioned at the beginning of the talk, some of this is joint work with Joseph Marr and Giulio Tiozzo. I should write it here. So theorem with Marr and Tiozzo is the following. For Lebesgue almost every gamma, limit t goes to infinity of the total excursion up to time t divided by t is infinite. So this limit is infinite. And on the other side, again, g and t. For h almost every gamma, the same quantity, well, I should write it slightly differently. There exists a constant bigger than 1 such that the limit as t goes to infinity, well, I'll just write it as there for such that for h almost every gamma, this quantity stays bounded between these two. For large times, for all large times. So with respect to these two measures, this is a good statistic to tell them apart. The statistic actually tells us that these measures are singular with respect to each other. So the corollary is a proof of the following theorem of Givart and Legendre, that H and Lebesgue are mutually singular.
So how do they prove it in a different way?
Essentially the same way they're looking at the asymptotic winding of a typical geodesic, which is what we are doing anyway. If you cross, if your excursion is a certain size, the winding that you would see in the cusp, around the cusp, is proportional to the excursion. So it's in spirit, it's the same proof, but their techniques were more analytic for some reason than we are doing sort of soft ergodic theory proof of this.
There's also for H2 only, or?
Okay, so the original paper by Givart, so this is sort of, in the original paper by Givart and Legendre, only certain subgroup of SL2Z was considered, but then everyone looks at the proof and says, oh, this should work in general, and that's never been actually written down. The whole point of this is that before, there is this analogy with the mapping class group, and what I'm saying here essentially carries out exactly in the mapping class. That you can, I'll get to that in certain, there's a certain quantity, there's a certain statistic that one can watch along Teichmuller geodesics, and that these two theorems hold in that setting. So there is more hypothesis for obviously for mod S, which I'm not going to say, but this should be the takeaway line, that this actually
And what
works.
about this? This is really, there's no limit? I mean, what
So we have to tweak these quantities slightly. So actually I should have mentioned, the total excursion up to time t, you should think of it as a low, that's a coarse lower bound for the growth of word metric. Okay, so remember up here, what was the total excursion was doing was somehow measuring the distance along the geodesic in the thick part. So you're taking the geodesic, goes through a bunch of parabols, project it all back out to the thick part and take the distance there. The thick part is quasi-isometric to the group itself. So you can think of the total excursion as trying to measure word metric along a typical geodesic. And if we replace this quantity by the word metric and the numerator by the relative metric, essentially you want to apply some ergodic theorem which will get the limit out. And just as it stands, there isn't a limit.
Sorry,
Just as it stands, there isn't a limit. But if you just tweak this slightly, you do get a limit for the harmonic measure. Okay. All right. So yeah, and then the same thing sort of works in the mapping class group as well. The fact that these measures, the harmonic measure in the mapping class group case is singular with respect to the Maser-Rich measure. This was done in my thesis with a more symbolic dynamics kind of idea, and this is sort of more robust, more geometric.
What is U?
Uh,
G1 GN are sampled by U. What do you mean? What's U?
Sorry?
You write G1 GN are sampled by U.
Oh, by the distribution.
What is
By
mu?
there is mu.
What is mu?
It's stuck. Yeah, mu is the initial distribution for the random walk. Yeah, it's a probability distribution in the group. It's finitely supported. If you make the assumption finitely supported, that's simpler. You could have a slightly weaker condition as well on what mu should be. It doesn't have to. Finitely supported is the strongest condition, which allows you to stay the statement. But there are weaker versions of this that are possible, and then you just take a random walk on the group using this distribution. You get the measure at infinity, use the measure at infinity to sample geodesics. All right. So that is it. Next, very good. Now, okay. So now I want to focus more on the Lebesgue measure part. This theorem here tells us that the total excursion grows faster than time, and then you could ask, well, what is actually the growth rate of E gamma t? What is the growth rate of the excursion? So the theorem here is the following. Is there anything else that I wanted to say? All right. So in the Lebesgue measure case, theorem 3. For Lebesgue, almost every gamma. Now we take the following quantity, limit t goes to infinity. We take the total excursion and trim it by the maximum excursion in time t. So we take this sum and remove from it the maximum term. You take this quantity divided by t log t, and this has a limit as t goes to infinity, and the limit is very explicit. So it's 2 over pi times the volume of the thin part of x divided by volume of x.
The cusp density.
Is the cusp density. Yeah.
N is T, so K is less or equal than N?
So n here is a function. I mean,
So it's
I'm just
not-
enumerating. So I had somewhere here that the hi up to hn were the horoballs till time t. Okay, so this is like you have some number of terms up to time t, and you remove from it the largest one.
Mhm.
And when you trim it and then you get a strong law like this. Okay, so I should perhaps give some background from continued fractions. Yeah, this n is dependent on the geodesic actually. Okay, so this there is an n of gamma here.
I mean, n of t is basically t over the.
Yeah, this yes, of course, n of t over t has a limit as t goes to infinity for almost every geodesic.
And it's in fact that thing.
Yes. Continued fractions. So what were the results known for continued fractions? So the analog of theorem 1 for continued fractions is for almost every r in 0 to 1, the limit n goes to infinity of a1 plus a2. The sum of the first n coefficients over n is infinite. This essentially goes back to Gauss. The existence of the invariant measure for the Gauss map is enough to show this. Did I spell Gauss wrong? Anyway, I don't ever remember the spelling problem. Then Khinchin showed the following theorem, that the numerator grows like n log n in measure. Okay, so the limit n goes to infinity of the Lebesgue measure of all r, such that if you take the following difference, this is the continued fraction coefficients for r divided by n log n minus 1 over log 2. As if this deviation is large, so r is the set of points where this deviation is large, the limit as n goes to infinity of this is 0. So fix epsilon, the place where there is a large deviation in measure goes to 0. Okay. And the third theorem in this context was proved by Diamond and Valor, which says the following. So for Lebesgue, almost every r in 0 to 1, the trimmed sum has the right limit. So limit n goes to infinity, the sum of the ai's minus the max of the coefficients, k less than or equal to n, ai's, ak, over n log n. This has the limit 1 over log. So this is the strong law. So almost every state. Okay? And of course, this theorem will now be a special case of that theorem, theorem 3, by considering the case of the modular surface. So this theorem here is a special case of theorem 3. For the modular surface. And the only thing really is to figure out the limit as t goes to infinity of this quantity n. Okay? And that's sort of classically known. And then theorem is straightforward from that.
When was the diamond knighted?
Sorry?
When was it common?
This 88, 89, 1988.
86.
86. I think so there are some people in the audience who are more prepared for the talk than I am.
When's my birthday?
Yeah. Oh, all right. Okay, so I should give you some idea of the proof of theorem 3. And then I will, depending on how much time is left, what time? 11:50? Okay, so idea of the proof. So as with anything, we want to realize the total excursion as the integral over time of some function. Okay? So we take the following function. So we take so let P capital P now. Just take this to be capital P be the projection from the unit tangent bundle to X. We take the following function on the unit tangent bundle. So phi of V, this is defined only on the thin part. This is going to be 2 over pi e to the distance of P of V to the boundary of the hyperbole. Okay, if P of V belongs to the hyperbole. So H is a hyperbole. We take this function and it's 0 otherwise. So this is a function just that is defined on the tangent bundle over the thin part. And what's the point of defining this function is the following, that suppose we have a picture, let me draw the picture here. Here is R, here is the hyperbole. Okay, I'll draw the hyperbole here. Here is my geodesic that is doing an excursion in the hyperbole. Let's suppose the geodesic enters at time t1 and leaves at time t2. And our excursion is defined to be this distance here. That's our excursion. And so it turns out that the integral between t1 and t2 of this function, phi of v of gamma of t, gamma t. So this is the tangent vector, tt. This is equal to, don't write equal here actually, to the excursion up to a uniform additive error. And that additive error is 1. So this function actually captures excursions. So this total excursion is an integral over time of this function, but we are somehow removing something from it. So what are we doing? What we are doing is the following. Oops. Wow. Want. Okay. Here. So phi, this function phi is not L1, but this quantity, the numerator that we are considering, this numerator is very well approximated by a suitable truncation of phi. So it turns out that this numerator is approximated, and I'll explain what approximated means, like what is the error and so on, by the integral between t1 and t2, 0 to t, 0 to t of a suitable truncation of phi. And this truncation is actually time dependent. It depends on this t of v gamma t ct. So what do I mean by truncation? Phi is defined on the whole thin part, and basically so phi is defined everywhere here, and what we do is there is some level beyond at which you can truncate, and if this was imaginary part of z is equal to 1, this turns out to be imaginary part of z equal to t log t to the power c. It's not important what that is. There is some truncation that we can introduce, so that we just consider phi in this strip. Okay? And this quantity is approximated by the integral over time of that truncation. And of course, you want to apply the quadratic theorem, and you want to say that this is equal to t times, this converges to t times the L1 norm of this truncation. Okay. So now we have a limit theorem, so we must estimate the errors in all of these, right? So we want to know that when I say this is approximated by that, so it turns out the error here is linear in t. For this first step, it is linear in t, so when we divide by t log t, it is, and take limit as t
So
goes.
the function depends on the t. So
Yeah, the truncation depends on t. That's the certain
how do
point.
you use the position?
You have to prove, okay. So you have to prove, yeah. In a minute, I'll tell you in a minute. So this is approximated by an error which is linear in t, which goes away when you divide by t log t. And the error here, so what we need is an effective version of the ergodic theorem. We need something, we need a rate of convergence in the ergodic theorem, but now we are trying to apply it to a collection of functions, family of functions, which is also time dependent. So the error here turns out to be O of small o of t log t. And in fact, it turns out to be something like that, where c, so sorry, this c should be less than 1 and greater than 1/2. But anyway, there is some error here which also goes away when we divide by t log t. So we need an effective version of the ergodic theorem, and that uses exponential mixing of the geodesic flow. So to prove the effective ergodic theorem needed here, we need so for this statement here, we need decay of correlations. Make sure that I get correctly. We need exponential decay of correlations for SO2 are invariant L2 functions. So this decay correlations, I don't know, goes back to Moore and Ratner, but Eskin mentioned that it should be in SL2R by Lang as well or something. It's more standard anyway. This is quite standard.
I mean, this is just a fact about special functions, right? It's a fact about spherical functions of decay. And I mean, there's somehow two pieces. There's the fact that there's a special gap, which in this sake is automatic. It comes from some sort of elliptic regularity of some sort. And just because, you know, you have Laplace enacting on this,
Right.
there's going to be some special gap. And then once you have a special gap, then this is just, you can look it up in some 19th century textbook.
Okay. Anyway, so one has to use exponential decay of correlations. So basically, the idea is one wants to estimate the deviation of the ergodic average from the L1 norm. You take that function, you square it, you use the exponential decay of, you take the integral over the whole space, then use exponential decay of correlations to control that integral. Yeah. Anyway, so that, I mean, yeah, okay. So basically, one needs an effective version of the ergodic theorem. Right. So that, I mean, that's the idea of the proof. And now I'll talk a little bit about Teichmüller theory of why this has parallels in Teichmüller theory. Are there any questions?
Approximated, you mean like in L2 norm?
Or approximated, basically if you just, no, this is a pointwise, almost everywhere. So what is the point? The point is that the excursion, by this quantity, the excursion is the same as this integral x up to a uniform additive error. So the additive error that's going to come up from the excursions is related to the number of excursions you do. The number of excursions is a quantity that grows linearly in time. That's why you get this error, which is linear in t.
Maybe can you just say one word about why you exclude the biggest excursion? Maybe this is somehow maybe is there a way to see it?
I mean, it sort of relates to the Khinchin's theorem that, you know, along almost every sequence, every now and then we are going to see very large excursions. So you take, you know, something like if you require log n, for infinitely many n, this is going to be true along almost every sequence. So every now and then there is an excursion which is really large. the point of this truncation is that one can prove that the number of excursions that are bigger than this truncation is at most 1. So there is just a single large excursion which exceeds this threshold. And that's just the Borel-Cantelli argument. Basically, you show that excursions are independent by the exponential mixing, and then it's just Borel-Cantelli to show that there is at most 1 excursion that exceeds this threshold. And the point is that you see the contribution to E, actually when you have a large excursion, just basically you can ignore the parts that come from the strip. The contribution is mostly from what you do outside the strip, sort of above the strip. So that's why it's sort of truncating by just one term works here in this case. I mean, there is this theory of trim sums in abstract over theory, which I don't really know the theory very well, but sometimes for things which are distributed in some other ways, you have to maybe drop more terms to get a strong law. But in this case, you just have to drop 1 because you can show that there is at most 1 large excursion. All right, Teichmüller's theorem. But you sort of gave the answer to why this works in Teichmüller theory, because the point is that by Conservation and Zurich, there is a spectral gap for the Teichmüller geodesic flow, and that's why the same decay of correlations works there, and that's why you can basically have this machinery running. So anyway, I'll talk a little bit about Teichmüller.
So are these results for other locally symmetric spaces of this software?
I don't know. I mean, that's, yeah. There should be. I don't know. I mean, these are like, I mean, certainly the log laws is known in lots of contexts, and this is sort of finer questions from that perspective. So that yeah. Am I allowed to say that I'm working on it? Okay, so Teichmüller theory. So, okay, so S is going to be a closed orientable surface. Or one can take finite type surfaces as well. The Teichmüller space of S, Teich S, is space of marked conformal structures on S. The mapping class group is the group of orientation preserving diffeomorphisms of S modulo isotopy. Of course, the quotient is the modular space of curves. Modular space of even surfaces. We need one more space to define. Maybe I should define it here. Q is the space of unit area quadratic differentials. And this should be thought of as the tangent space, the unit tangent bundle over Teichmüller space. Okay, I messed this up. Can I just hold this maybe? All right. I don't know, it came out of this thing. I don't know how fix it.
Maybe you can thread it through your button.
Sorry?
Maybe you can thread it through your button so you don't have to
Just rub around.
Just run. That works. At least my talk is providing excellent entertainment. That's good. Yeah. So space of unitary quadratic differentials. So what does a quadratic differential do for us? It defines given a quadratic differential Q, one gets, so this quadratic differential Q equips our surface with charts to C and transition functions which are of the form Z goes to plus or minus Z plus C. This is called a half translation surface because the transition functions are half translations. Examples would be to draw the L-shaped table. So we have charts to C and transition functions which are half translations. So in this example, I'm going to use just translations and glue these sides up by translations. So you glue opposite sides by translations. This gives a genus 2 surface. And so the quadratic differential equips the surface S with this structure. This defines a flat metric on the surface with some cone singularity where there's a negative curvature go. The negative curvature goes when you identify this point. This point will have 6 pi angle around it. All the negative curvature goes at the cone singularity. So this is a flat metric on S with cone singularity. Just by the way I have drawn the picture, it's clear that there is an SL2R action on Q. I should say that the space Q the space of quadratic differential is naturally stratified by remembering. So a quadratic differential it's a holomorphic quadratic differential. It has some number of zeros and poles. We insist that the poles actually occur at the punctures of the surface. So if you have a closed surface, it just has some number of zeros, and we could remember the multiplicities of the zeros. So it gets stratified by actually remembering the multiplicities of the zeros, where k bar is going to be some tuple of positive numbers which just add up to the right thing. 4g minus 4, where g is the genus of the surface. So we have your quadratic differential has a bunch of zeros, and those all the negative curvature is concentrated at the zeros, and the space gets stratified this way. And the SL2R action on the space of quadratic differential is just in this picture. This picture is in the plane. SL2R, there's a SL2R action on such a picture. The transitions are preserved by this action. These transitions are by half translations, and they're preserved under SL2. So it preserves gluing. So we get an SL2R action on Q. It's clear that if you just take the rotational part, so the compact part does not change the underlying conformal. Conformal structure. So this means that so Q, we have to think of this bundle as Q over diagonal space. There is SL2R action here, and the compact part does not change the conformal structure. So one gets an embedding. So we take we get a hyperbolic plane sitting inside diagonal space. These are called diagonal disks. So diagonal space is now foliated by these diagonal disks. And notice that the SL2R action actually preserves the stratification of the space. So there is an action, one should really think of as SL2 action on each stratum of Q. Moreover, each stratum carries a natural measure class which should be thought of as a Liouville measure just by taking the period coordinates. So in this picture, there are a whole bunch of segments which are interesting. For instance, this one here, this is called a saddle. A saddle is going to be a geodesic segment in the flat metric which connects two cone singularities. So a saddle is a geodesic segment in the flat metric.
You study saddle connection. Saddle seems a saddle.
Saddle connect. Okay. Flat metric connecting two singularities. They could be the same or distinct. And so one could take the periods associated to saddles, and those become coordinates on, should take the relative homology and take periods of a basis of relative homology, and as you vary Q, that gives coordinates on the stratum. So this defines a measure on the stratum which is called the Maser-Weich measure, which should be thought of as the analog of the Liouville measure in the earlier setting. Okay. So this considering periods gives us a measure which I'm going to call as mu holonomy. This is the Maser-Weich measure on the stratum. And the point is that the conditional measure that this induces on a Teichmuller disk is exactly the Liouville measure on the Teichmuller. Remember, Teichmuller disks were these hyperbolic planes sitting inside Teichmuller space, and the conditional measure is exactly the Liouville measure on that disk. Okay, so what is now in the earlier picture we had all these horoballs. Where are the horoballs in this picture? So what one does is the following. So we look at this following set. So we fix a saddle tau. So in this case we could fix various things, but fix a saddle tau. It could be I should say saddle for the expressive model. It could be a cylinder. It could be a cylinder with area at least delta, etc. So we fix such a saddle, fix a tau, and we look at all quadratic differentials Q prime in the SL2R orbit of Q, such that in the flat metric induced by Q prime, tau has really short length. Tau is really short.
So once again, you have saddle connection.
Yeah, it's a saddle connection. So, but there are alternate sub-collections that one could consider, which are called, anyway, I won't get into that, but just ignore these other two words and consider saddle connections, and then one can look at, in the SL2R orbit of Q, one can look at quadratic differentials where the saddle becomes really short in the flat metric given by that Q prime. This thing projects to a horoball in the Q. Oh, I should have mentioned, I told you about the compact part. The diagonal part is the Teichmuller geodesic flow. The action of the diagonal part is the Teichmuller geodesic flow. And so, what is the point at infinity for the horoball, for this horoball? Imagine, so we have a saddle on this surface. First rotate this surface so that this saddle becomes vertical. So that's some E I theta Q. That's some other quadratic differential, and now apply the geodesic flow. The geodesic flow will shrink the vertical and expand horizontal. The diagonal part will shrink the vertical and expand horizontal. So in the limit, the saddle will shrink to length 0. And that's the point at infinity for this horoball. Right? So, okay, so now our Teichmuller disk comes equipped with a lot of horoballs, in fact, too many in some sense. The intersection, so if you think of this as the thin part of Q, the intersection of the thin part of Q with each Teichmuller disk is very complicated. But okay, so you have this horoballs, and one could sort of try to run the same machinery up there. And so the theorem is that, this theorem. The whole attempt here is to at least try to show that somehow this analogy is really strong because of these Teichmuller disks. So the theorem is that along a typical Teichmuller geodesic, for mu hall almost every Q, if we consider the same quantity, t goes to infinity, of the total excursion in these horoballs up to time t minus the maximum and we divide by t log t. This quantity has a limit, and the limit is actually related to the Siegel-Weich constants of the strata. So there is the Siegel-Weich constants of that strata are going to show up on the right hand side. So there is something like it's 2 over pi times the Siegel-Weich constant. I won't write exactly what the limit, but anyway. So the Siegel-Weich constants sort of tell us the volume of the thin part of qk bar as epsilon goes to 0.
But you were saying you're not consider all horoballs.
Oh, okay, so you could consider sub-collections of this. So there are 3 versions of this theorem. You could just consider saddle connection, all saddle connections. Then the Siegel-Weich constant for the full stratum will show up. One could consider cylinders. Then the different Siegel-Weich constant will show up. And one could consider cylinders with area below, and then the third constant will show up.
You can do it for all.
You can do it for all, as long as you the thin part you're considering is as long as it has good equivariance properties for the mapping class group, that should be the machinery should work. Yeah, I think I'll stop here.
Okay, so any questions?
Do you have a paper?
Give me one thought. I mean, if there's I could send you a preliminary draft of it.
Yeah.
It should go on the archive in a month.
Just one remark. I mean, you said spectral gap in this case was due to Kontsevich and Zorch, but it's actually, I think, due to Avila, Guzel, and Yokos.
Oh, I sorry, I meant the Kontsevich-Zorich conjecture, which was proved by Avila, Guzel, and Yokos. But it was proved for abelian differentials by Avila, Guzel, and Yokos when Avila and Rezande for quadratic differentials. So yeah, the existence of spectral gap in all strata of quadratic differentials. But anyway, the point is that once you know that, then this exponential decay of correlations that we need holds, and then the rest of the argument essentially follows. Same one.
Okay, so let's
Yeah, but I mean somehow it's just not. I mean it's just natural to bring into this. Somehow all you really is a volume estimate. I almost want to say that it's true in every technical disk, and but it's certainly true in almost everything. But you're right, it doesn't, I just wanted to bring the fact that there's an asset or action and I'm using the same kind of expression.
Yeah, the stakeholder does. I mean, the fact is, of course, there's this theorem about St. John's that says that each direction is for often a solid that's regular, but that may not be irrecurrent in every single disk.
Do you have a, yeah, would this thing actually be true in almost every, in every regular disk?
Yes.
Friday.
No kidding.
Well, I mean, you should do this.
This ergodic theorem was a rate.
You just got back from
Yeah.
St. Petersburg.
You need, yeah,
Apparently,
you need some reasonably strong.
his wife was mum the previous week.
Makes
Wasn't very nice.
You,
okay, so you were not.
You care about
No,
essentially the same problem that
weather was
we
nice.
have for cognitive
There was a
stuff.
Hockman thing.
Geodesics can do.
Right.
Circle
I had
averages.
a
Yeah.
bunch of
Yeah.
players
Yeah, that's right.
And we don't even, never mind the race, don't even know.
Oh, I see.
He's not taking circles.
There's a long
Oh, no, that's,
I just need it for GPA. I don't have to, right?
For every typolar disk, the Birkhoff theorem holds some nice rate.
First, yes.
In almost every.
Exactly.
Yeah.
That's the
Okay,
second.
let me think about this. So,
Somewhere
In your
close to
paper,
the
John, you
Amazon
proved that
falls.
Birkhoff holds.
yeah, so I think we do something non-effective there.
Oh, I see.
That's what my, I mean.
But it's the Hebrew.
I mean, also, in some sense, it is probably
Yeah.
really true, but without any condition. Imagine the technical business is very close.
Sure.
Yeah.
And then so for a very long time, you're going to think you're, so in that
Yeah, and
moment,
then, yes.
and then you're not going to, but I mean, on the other hand, that's the limit as t goes to infinity by solution.
Yeah.
But somehow it's not really clear what I mean by uniform.
Yeah, I mean, I did, the way I've written it right now, it's like almost every technical disk, just because I don't know what is the precise algorithm.
So he actually traveled to St. Petersburg.
I mean,
It's of course, you could axiomatize your statement, you could say for almost every, with respect to any measure, SL2R invariant measure.
that's
with a
actually a
spectral
good,
gap.
yeah, any SL2, this got, I mean, but
Yeah, it's
how,
hard
do you
to
know the
know,
same
yeah.
decay rates for the two parts? For any SL2 in that?
Well, for any satisfied, what you should do is you should axiomatize it.
No,
You
but
should say,
wait,
suppose you have this regularity condition and the spectral gap,
Yeah, really chance.
and then you can try and verify it for other SL2R invariant measures.
So the spectral gap works for other results, right? That's probably the point of it.
I need the thin part, I mean, you need to go to the thin
Regularity.
part has a certain kind of,
But that's also,
decay.
that's just equal.
So all the rest
So
of
the,
the gang was
but basically I
there?
need that the single reach.
I bet you were still coming
That
out
works
from-
for every
from
network.
St.
Okay,
Petersburg.
so then that should be,
It-
so that you have like, you know,
You may
if
not
you make
know.
a saddle like less than
It's
silent,
bad
then
hair.
you want to know that
C times
keeps
epsilon
that
squared.
That's the volume notice that.
For the volume of thin part less than epsilon is equal to C times epsilon.
Or is equal, is
It's,
asymptotic.
no, where the error term is smaller than
Spectral gaps in the
Oh,
rotation.
it's smaller.
Yeah, I think this is regularity.
But this is even, I think this is softer. Because this is just asking the,
Which was a nice
because you're looking at the
relief
measure of
from
set of guys
differences.
with alpha connection epsilon. That should behave like z equal to h times epsilon squared, right?
Okay, maybe, but on the other hand, it's definitely in this paper by Mateo cause of regularity.
So am I to conclude?
Yeah, I mean,
that's
so
true.
one answer is that one, if, I would be nice if I could say this for every
No,
technical
I try to broaden my interest.
But certainly you should be able to say for almost every
It's
with
always a
respect
pleasure
to
to meet people.
Any
chat to them.
any nice SL2R invariant measure, and I think probably all SL2R invariant measures are nice in your sense, spectral gap and right decay.
Well, no, I don't think I don't think you're right. I mean, I think most things that are true for strata are also true for us. I think at this point,
Yeah,
there's almost
I mean,
there's almost nothing that. But every point is like I think probably.
She was actually going hunting with the end of the year, so I thought, maybe.
That's very nice.
She survived.
You want to go for that?